The human body is more complicated than the most complex machine. A power station constantly burning fuel, producing energy, doing work. A chemical works, taking in food, breaking down some molecules, building up others. But like any machine, our body needs control mechanisms to work efficiently. Many of the body's vital processes require a controlled environment to work at all. This is the concept of homeostasis, the mechanisms that work together to enable our bodies to maintain a constant internal environment. But we often put our bodies in situations that threaten this delicate balance. And in this program, we'll be looking at how our bodies respond to one of the toughest tests of all, the marathon. The place is Amsterdam in the Netherlands. The time, early autumn, or to be more precise, 10 a.m., September 24th, the morning of the Amsterdam City Marathon. As the runners limber up, they know how important it will be to maintain the body's chemical and physical balance in the race ahead. If at any point in the 42 kilometers of the marathon course they go beyond their limits, disaster lies in wait, and it will for many of them. But what are these limits, and what are the changes and challenges our bodies face if we want to run continuously over such a long distance? Over 2 hours for the fastest, and more than twice as long for those at the back of the field. There's only one way to find out. Select a single runner and follow her through the course of the race. So what do we need to know about our athlete? She's 1.64 meters, weighs 68 kilograms in her running gear. Her resting heart rate is around 62 beats per minute, and she's breathing at a rate of 14 decimeters cubed per minute. Her core body temperature is 37.2 degrees C, the skin temperature is lower, and the blood glucose level 90 milligrams per 100 centimeters cubed. Right, let's standardize them for the start of the race. This will be the normal level, and these are pretty normal figures for a fit person. So weight, heart rate, breathing rate, temperature. They'll all be good indicators of the mechanisms at work in her body as she runs. We'll keep an eye on them, any significant changes, and we'll get a warning. But while Martina prepares for the race, there are a few things you might want to think about. What changes would you expect? Many people don't finish a marathon. What danger signs will you be looking for? And how will changes in one indicator affect the others? Okay, 10 minutes before the start, and Martina and many others are having trouble with one homeostatic mechanism. It's hot, and they know it's going to get hotter, so Martina's making sure she drinks plenty of water. She doesn't want to become dehydrated later in the race. But take on too much water, and there are inevitable consequences. Like everything else we're looking at, it's all a question of balance. Just a few minutes to go and everyone's getting tense. First warning light, heart rate, time for a body check. Weight, temperature and blood glucose levels, no change there, but there is a slight increase in breathing rate and a much bigger increase in our heart rate to 90 beats per minute. But she hasn't done anything yet. What's going on? The first of the control mechanisms has kicked in. It's located here. These are the adrenal glands, one on each kidney. These glands are well supplied with blood vessels. And a hormone called adrenaline is released from the adrenal glands into these capillaries, The adrenaline is carried around the body in the general circulation. It affects several organs. The heart speeds up, and the liver breaks down its energy store, glycogen, into glucose, more fuel for the muscles. Martina hasn't asked her body to do more work yet, but already her body's prepared. More blood is being pumped, more fuel made available. Now you know why commentators say the adrenaline's really flowing now. Time to start the race. And just to show that we're not making this up, one last check on her weight. 68 kilograms. But will it be the same at the end? 42 kilometers to go. And they're off. The start of a marathon is very important. With so many runners around, it's difficult to start at the correct pace. Too quick and you suffer later on. Too slow and you get a poor time. We're getting more warning signs. She's only 1 kilometer into the race, so what's happened? Let's look at the chart. A slight drop in blood glucose levels. She's obviously using fuel. But a big increase in heart rate to 140 beats per minute. And her breathing rate has gone up too. It's almost doubled. So her heart and her lungs are working harder. What's the connection? As soon as Martina started running, her muscles were working. They needed more oxygen and produced more waste gas. So the oxygen supply from the lungs must be involved. She breathes more rapidly and more deeply. In the air sacs in the lungs, the rate of gas exchange increases. More blood, more oxygen, more carbon dioxide. More work for the lungs. But also more blood needed to carry oxygen to the muscles. The heart has to work harder. It beats more quickly. The heart rate increases. It's also pumping more with each beat. The output is 4 times greater than at the start. So Martina's body has responded to the first challenge of the race. Before the race, her heart rate and breathing rate were balanced to supply sufficient oxygen to her body while it was at rest. But as soon as she started running, she knocked the system out of balance by making her muscles work harder. Now her body's responded. Her breathing and heart rate have stabilized at a higher level. It's the same for the other runners. The question is, at the quarter distance mark, can they keep it up? At 10 kilometers, most of the runners take their first drink, usually just plain water, although some choose drinks containing glucose. But most of them don't feel particularly thirsty, so why bother? After all, it isn't that easy. Think about it. It'll become important later on. Here's Martina at the feeding station, and we've got another warning. It's a temperature warning, so what's going on? Time to use a bit of technology. This thermographic image of Martina was taken at the start of the race. It shows the temperature of her body surface. The hottest areas shown in red and orange. Her face, neck and arms. Cooler regions show up in yellow. The coldest parts of her body, her hair and fingertips, show up as green or blue. The blue and green on her body is in fact her running vest. Now compare that with an image taken just after the feeding station at 11 kilometers. Spot the difference? The exposed areas of Martina's body are hotter, more red areas, or white where the body is hottest. Most obviously the shoulder, arms and legs where the muscles work hardest. When muscles contract, they produce a lot of heat energy. That's what we're seeing here. And that heat causes the body some serious problems. This is a blood vessel. Heat from the surrounding muscle warms the blood. It's carried into the general circulation, raising the temperature of the vital organs. This is the core body temperature, and if this becomes too high, the body's chemical reactions will cease to function. So the body has conflicting demands. The muscles need the increased blood supply to keep working, but the heat they generate will warm the body to dangerously high levels. So how do you stop that happening? Well, you could stop running, but that would defeat the whole object of the race. Any better ideas? Well, let's start with the blood. This is where it flowed before Martina started running. Muscles, 20%. Digestive system, 25%. Kidneys, 20%. The brain, 15%. The skin, 5%. Heart, 5%. Rest of the body, 10%. What's happening now? Brain, still 15%. Heart, 20%. Muscles, 50%. Skin, 10%. Rest of the body, 5%. So the body has responded and sent blood to where it's needed most, the muscles, heart and skin. But Martina needs to cool down, so why not send even more blood to the skin so that excess heat is conducted to the surface and lost into the atmosphere? Good idea, but there's a snag. Send more blood to the skin and there's less available for the muscles. No blood for the muscles, and you can't carry on running. Any better ideas? Well, cooling the body down must involve the skin. It's where the body comes into contact with the world outside. If more blood can't be sent to the skin, how can it help to cool the body down? There are two ways for a start: radiation and convection. This is an infrared image. The body looks as if it's glowing. Heat is radiating from its surface, but obviously not enough heat. What about convection? As she moves through cooler air, heat is carried away from her body surface. Run faster and more heat is lost. But move faster and you generate more heat. Catch 22. So what's left? Heat loss by evaporation. Good old sweating. These are sweat glands in the skin. The brain senses any increase in temperature and stimulates the sweat gland. Moisture is released. Moisture, evaporation. And evaporation carries heat away from the body. It causes cooling. Back to the thermograph. Martina's body is hot. But her running vest is much cooler, a result of the evaporation of the sweat collecting in the fabric. That sounds great. Turn on the sweat glands and lose the heat generated by the muscles. Easy. Well, not quite. Sweat and you lose water. That makes the blood thicker and harder to pump. This is dehydration. Let it continue and your body would cease to function. And that's why Martina is so keen to replace water as quickly as she's losing it. And remember, she drank a lot before the race. Now it's paying off. She's moving through the field. We're now over half distance, and some of the less experienced runners are struggling. Too hot, too dehydrated, too little training. It's hard to say why. Back in the race, more and more runners are choosing glucose drinks. Another warning light, this time fuel. Muscles depend upon a constant supply of fuel, particularly glucose. But where does it come from? There's a little in the liver and the muscles, most of it in the form of glycogen. But 30 kilometers in, and the glycogen has been used up. Martina is now depending on another source of fuel, fat. Fat stored under the skin and inside the body. When the level of glucose in the blood runs low, fat is broken down to produce glucose, which can be used by the muscles. When they started the race, these runners used their primary fuel, carbohydrate in the form of glucose. Now they've switched to the reserve tanks. They'll finish the race running on fat. The leading runners are approaching the finish. 42 kilometers covered, a triumph for each of them. Other runners are still on the course, as much as 20 kilometers behind. But for Martina, it's looking good. Only a few runners ahead of her. A change of weight. Martina's weight has dropped from 68 kilograms at the start to 63 kilograms. She's lost 5 kilograms, enough to trigger our alarm. Why? It's all that sweating. She's lost 5 kilograms. That's 5 decimeter cubed of water. But if she doesn't sweat, she'll overheat. The answer lies in the kidneys. Sensors in the brain detect that the blood is becoming too concentrated. These are the receptors. A hormone is released into the bloodstream. This causes a response in the kidneys, the effectors. As a result, urine production is reduced. This means a reduction in water loss. Blood levels return to normal, an example of negative feedback. For these runners, the test is almost over. Their bodies have overcome the challenge. The finish is in sight, and here comes Martina, her pace over the final stages bringing her up to third in the women's race. But as she takes a well-earned drink, replacing the 5 decimeters cubed of fluid she's lost, let's recap on the homeostatic mechanisms that have brought her this far. First, the brain. That's what made her run in the first place. It also houses the temperature receptors and detects changes in blood concentration. Adrenaline released into the blood to give the kickstart. Then there's the muscles. They upset the balance in the first place. The heart and lungs increase their activity to supply oxygen via the bloodstream. The liver to store glucose and to break down fat, the secondary source of fuel. The kidneys, the regulators of water loss. In fact, the whole body. And this particular body has done a whole lot of work. The human body is more complicated than the most complex machine. A power station constantly burning fuel, producing energy, doing work. A chemical works, taking in food, breaking down some molecules, building up others. But like any machine, the place is Amsterdam in the Netherlands. The time, early autumn, or to be more precise, 10 a.m., September 24th, the morning of the Amsterdam City Marathon. As the runners limber up, they meet a single runner and follow her through the course of the race. So what do we need to know about our athlete? She's 1 meter 64, weighs 68 kilograms in her running gear. Her resting heart rate is around 62 beats per minute, and she's breathing at a rate of 14 decimeters cubed per minute. Her core body temperature is 37.2 degrees C, the skin temperature is lower, and the blood glucose level 90 milligrams per 100 centimeters cubed. Our body needs control mechanisms to work efficiently. Many of the body's vital processes require a controlled environment to work at all. This is the concept of homeostasis, the mechanisms that work together to enable our bodies to maintain a constant internal environment. But we often put our bodies in situations that threaten this delicate balance. And in this program, we'll be looking at how our bodies respond to one of the toughest tests of all, the marathon. Know how important it will be to maintain the body's chemical and physical balance in the race ahead. If at any point in the 42 kilometers of the marathon course they go beyond their limits, disaster lies in wait, and it will for many of them. But what are these limits, and what are the changes and challenges our bodies face if we want to run continuously over such a long distance? Over 2 hours for the fastest, and more than twice as long for those at the back of the field. There's only one way to find out. Select